Welcome to this hands-on tutorial on how to build the UFS Short-Range Weather Application version 3 from pre-built containers and how to run an out-of-the-box test case. I'm Priya Pillai, a member to the Epic user support team. To start with a brief introduction, the Unified Forecast System is a community-based, coupled, comprehensive Earth modeling system. NOAA's operational forecast models for numerical weather prediction is quickly transitioning to the UFS. Therefore, the UFS enables research and development within the broader numerical modeling community, which include collaborations from public, private, and academic sectors. For these reasons, community contributions are highly encouraged. Earth Prediction and Innovation Center brings together the broader numerical modeling community in an effort to produce the most accurate and reliable operational modeling system. In this line, EPIC supports and accelerates improvements to the UFS through open collaboration, code sharing, trainings, and user support. There is an EPIC website, which is also known as the EPIC Community Portal, and the users may find lots of useful resources at the website. And the website is hosted at epic.noaa.gov. This is the EPIC website where you'll find lots of information that is needed for the user. The most important documentation that is available is the user's guide. There's a get code page and a get support page. How to browse through these different pages, there is already a video tutorial that's available. If you go to the user's guide, there is a section that says how to run the container-based application. UFS applications are UFS configurations that support a particular forecast requirement. They vary in terms of temporal and spatial scales. Short-range weather application is an application that targets the predictions of the atmospheric behavior on regional spatial domain and on timescales from minutes to several days. SRW application include a prognostic atmospheric model, pre- and post-processing units, and a community workflow for running the system end-to-end. The SRW application assembles a variety of components which include UFS pre-processing utilities or UFS utils. It creates a regional grid on which it also creates orography and surface climatology files. The major component of the SRW application is the UFS weather model. The UFS weather model includes a finite volume cubed sphere dynamical core configured with a limited area model. The limited area model is to generate the grid for regional domain. The die-core is the computational part of the model and it solves the equations of fluid motion. The components of SRW application also include a unified post-processor or UPP to help process raw output from a variety of NWP models which can be used for visualization, plotting, etc. The Model Evaluation Tool Plus is a set of statistical verification tools which is to assess and evaluate the performance of the NWP. And there is a unified workflow tools which is a modern and open source Python package. It automates common tasks needed for many standard NWP workflows. So we will be discussing in detail about these components during the next tutorial. This tutorial is designed to walk the user through how to build and run the SRW app version 3 container. Normally, building and running the application vary from system to system. However, the container-based installation reduces this variability and allows for a smoother build experience. Why it is so? Container is actually a portable, consistent, and reproducible package, and it contains everything, sometimes almost everything, needed to run the specific application. This includes the application source code, required libraries, dependencies, configuration files, environment variables, and settings. And in this tutorial, we are attempting to build and run an out-of-the-box weather forecast for June 15 to 16, 2019 using a pre-built SRW application version 3 container on a Singularity or Apptainer runtime. For this simulation, the configuration used are predefined 25 km continental US grid and a global forecast system version 16 physics suite, FV3 based GFS raw external model data for initialization. This is an out-of-the-box case, and therefore the configurations are made simple and it is already provided. To build and run the SRW application version 3 from a container, users need to have access to the pre-built container images, which include all the required software. Ubuntu 22.04-indel-srw-release-public-v3.0.0.image is the SRW app pre-built container image name. They are available to download from the following machines or spaces supported by Nova. And these machines include Derecho, Gaia C5, Gaia C6, Jet and Nova Cloud, Orion and Hercules. Also, users who do not have access to these systems need to download the container image from the Epic community portal, and I'll be showing that in just a moment. External users need to download the container image and input data from Nova's S3 data bucket on AWS, and the location is shared here. Users need to download 3 files. One is the container image file for version 3, and there are 2 files under the out-of-the-box folder. One is fixed data file and the other one is the GST file. These two are the input files that is required to run this experiment. These files are available as zipped tar files. That's why the extension TGZ. External users or individuals who do not have access to the level 1 Nova systems need to install the following prerequisite softwares before attempting to build and run the SRW app version 3 container. All users must have an Intel compiler and an MPI. MPI is the message passing interface, which is an open source and standard parallel programming. And the locations to download these are also provided here. Users also need to download the Recorder Workflow Manager provided here. Users need to download the Recorder Workflow Manager to take advantage of the automated workflow options, and they also need to download the Singularity or Apptainer container runtime. I'm now logged into Hercules. It's a Nova supported RDHPC system, and I'm using clear command to clear the screen. Now I'm using the cd command to change my working directory. Users can use their own path. Using pwd command, I'm listing the present working directory. And now I'm going to create a new directory named temp.dir using the makedir command, and under which I'll be creating 2 new subdirectories, temp and cache. They will be the temp and cache for your Singularity container runtime. If you don't specify these temp and cache directory, it will automatically get created under your home directory, which is not desired. Now, after creating these, I'm going to set 2 new environment variables here, just to make sure that Singularity container runtime knows where the temp and cache are located. And using the export command, I have specified these paths here. And now I'm going to create a new directory for my experiment, and that I'm going to call it SRW v3c to make sure that it is for version 3 container. I am now creating a new directory to copy my input data here, and using cd command I'm changing my directory to the newly created data directory. Here I'll be running the wget command to copy the input data GST and fix input data. And if you have already copied these files using the download option, then you don't have to do this command. You can just move it to the location from where the Singularity command or Singularity container can access the data. So once you get the data, you know it is packed, and it has that extension .tgz. Now it is time to unpack the data using tar-xef command and list the data. You can see unpacked data for GST, and if you list it, it contains the input initial condition and lateral boundary condition files that is required to run the model or the application. And now untar the fixed data. Fixed data contains the orography climatology like files, and these two are the inputs required to run this out of the box experiment. Then we need to remember this path because we need to specify the input data path in the config.yaml file later. After copying the input data, the user need to change their working directory to the experiment directory and list it, and there is no files yet. Now export that to a variable so that you don't have to reference the entire path every time you have to reference it. Using echo command, you can see that environment variable here. I gave the name SRW v3c, which is same as my experiment directory name. And now we are going to see the image file. It is located under work directory on Hercules and Orion. The path is already given. For external users, they can download the data from the Amazon S3 bucket. That is, location is also there, already shared with them. Now export that image path with the image name to an environment variable called img. Hereafter I'm going to call it image, which actually represents the container image environment variable. Now it is time to load the Singularity module using this command module load Singularity, so that we can use Singularity commands. And now we are going to mount our local working directory to the container and copy a file from there. So use this command Singularity exec -b, my working directory or experiment directory, and use the same name for the container working directory, or to actually you are going to mount your local directory to the container and copy a file from a particular directory in the container to your local space. We are actually going to copy stage-srw.sh to our local directory. Now list the content. You can see there is this file listed, and the present working directory, if you see it, it is the experiment directory. Since the Singularity module is already loaded, we are going to see the content of the image using the following command: Singularity shell $img cd/2, go to the home directory of the container, list the content using ls command. You can see the files and directories, etc., that is in the container image. Exit the container using exit command. Now it is time to see what modules available. We already have listed the prerequisite modules. So in the Hercules system, we already have the modules available. So users who does not have, they have to download it to their local working directory so that they can access from the local working directory. Now we are going to load the module for Intel compiler. I'm going to use Intel compiler version 2023.2.4 and also loading module for MPI version 2021.13.0. We already have copied the stage data here, and now using the stage-srw.sh script, we are going to stage the container to our local working directory. That means you are going to copy the files from the container to the local working directory. For that, we have to use the script as /stage-srw.sh and -c to specify the compiler that we are using, and -m to specify the MPI version we are using, and -p is for the platform. Here I'm running this on Hercules, that's why I have given that name. And we already set the variable for container image, which is img. So I'm using -i option as $img. Now it is copying the data from SRW application repository from the container to the local directory. The command to copy SRW app repository from the container image has been successful. Now that we are exploring the content of the UFS SRW app directory that we copied from the container, we know the most important directories are located here, and push directory is one of them. The configuration file, etc. will be there, and the module files, different module files to simulate the workflow on different machines or platforms are also located under the module files. So first you have to use the command module use and give the path of the module files. Following that, use the command module load workflow underscore Hercules. Hercules is my machine. If you want to see the different module files that is available under that directory, just use the list command, and you can see different workflow files, simulation files are located there. Now that it is time to modify the configuration file, for that you need to change your directory to the USH directory, and for that give the entire path, list the configuration files there using the wildcard star ls command wildcard star, and here if you list the configuration files available, you can see config.community.yaml there, and copy that file using the cp command cp config.community.yaml to config.yaml, and from there we open the config.yaml file. Using the vi command we open the file, and there are multiple fields that need to be modified here to run this experiment. First is the user section. There is a machine field where you have to change it to your machine. Here I am using Hercules, that's why I'm going to change it from here to Hercules here. And then there is an account field. This is like a general placeholder that you can change according to your account or group. For that, you can come out of this file using the :wq to save the file and exit. See what groups you are in. You can use the command groups. For me, there are two groups, Epic and Nova-HPC. I'm going to use Epic in the field there. So coming back to the file, we are going to change the account field here to Epic. Now we need to modify the workflow. We are going to change it to true because we are using cron relaunch. So to use that, we need to modify the relaunch time as well. So need to add a new field here, which is cron underscore relaunch underscore interval intval underscore minutes, that is MNTS colon space 3. That means every 3 minutes it will try to relaunch the cron job so that it does not go dead. And there are date field which is already modified according to this experiment. So users for this experiment, they don't have to be modified. If you come to the external initial conditions and boundary conditions file, now it is time to modify the initial condition files because we already copied the initial condition files, that is the input files, to our local directory. So we can add it here. So it is like you need to introduce a new field here, which is use underscore user underscore staged underscore external underscore files. This is to indicate that we are using our own external files, and set it to true. And we already know that where our input files are located, so give that path. Now coming to the lateral boundary condition, they both are located at the same place, so you need to set the external file use is true, the command use underscore user underscore staged underscore extern underscore files to true, and then modify the field for where the base directory is located for lateral boundary condition. Now that has been added, and there is no other modification that you need to do for this experiment. Save these modifications and exit the file. Because here we are not going to do any post-processing or plotting. Walk the user through how to run the model using a pre-built container. Now it is time to generate the workflow using the generate underscore fe3 lam underscore workflow.py script. You can use the list command to see if it exists in the list directory. It automatically gets copied there and no need to modify. Using the / command, just submit the Python script there, and you can see it generated some messages on the screen on which you can see the experiment generation is complete. And now we are going to change our directory to test underscore community. I have changed the directory now, and if I am going to list the files there, I can see orography, any other directories already got generated. To see the status of that task, you can submit the regoto stat command here at this directory. All your output will be stored here. And as I mentioned earlier, focus of this tutorial is not to walk you through the post-processing or plotting part. This is how to run a container-based, pre-built container-based SRW version 3 application. Thank you for watching this video tutorial. We have now completed the container-based tutorial on SRW application. And if you have questions, email us at support.epic@noaa.gov. Also, we would like to bring your attention again to the Epic website or Epic community portal, where you can find lots of resources which include developer resources and user community resources, such as asking a question, reporting a bug, or posting an issue at the website, so that an SME, internal, or depending on the complexity of the issue, an internal SME or an external SME will be working with you to resolve the question. That's all. Thank you. Thank you for watching the video.